Now, test, test. Okay, so audio is working and the screen. Okay, so today, or this is the video for lesson 36, exercise 36, oblique asymptotes, and then solving equations graphically and algebraically. So let's start with the examples here. So recall, so in previous lessons, whenever there was like an equation that we had to solve using the graph, there were kind of two ways of doing it, right? So whenever you're given an equation, you can make it equal to 0, right? Make one side equal 0, so you move everything over to the left or everything over to the right. So you can make it equal 0 by moving everything over. You would then graph the function and then the solutions would be the x-intercepts. And the solutions would occur at the zeros or the x-intercepts of the graph. Okay, so we've done that before. So that is still an option for you. So if it's easier for you to graph this, so if you move this 3 over to this left-hand side, it would become -3. And you could sketch 1 over x plus 2 minus 4, and then sketch it on our graph and find the x-intercepts or the zeros of the function. And then that's one way of solving it graphically. And then in other cases, to solve it graphically, you would just equate the left-hand side to be one line, equate the right-hand side to be one line, and then sketch, and then where they intersect is another way to find the solution. So let's do it that way in this case. So looking at y1 equals 3, which is one side, and then the other side is going to be 1 over x plus 2 minus 1. Okay, and then this becomes a question from the last couple equations, right? So this one's easy. So let's, y equals 3 is going to be our y1. And then we get our 1 over x function, right? And then we have an h and a k, right? So we're moving it 2 to the left and 1 down. So remember the asymptote is normally at x equals 0. So now my vertical asymptote is going to be at x equals -2. My horizontal asymptote is shifted 1 down. So this is at y equals -1. Okay, and then we can plot some convenient points for us, right? So again, we want to test on both sides of our vertical asymptote. So let's test f of -1. So f of negative 1 inside here would be 1 divided by negative 1 plus 1, which is 1. So you get 1 over 1 minus 1, which is 0. So we actually found one of the zeros here at negative 1, 0. And then again, using my symmetry rules, I can tell that if this is a point on my graph, then f of negative 2 is going to be at negative 2, right? And again, substitute, negative 3. F of negative 3 is negative 1, negative 1 divided by negative 1 is negative 1, and then so negative 1 subtract 1 is negative 2. And again, you could use symmetry. And so if we were to draw a sketch graph now, we have our asymptotic behavior, so it's going to approach our asymptotes. And so let's sketch this a little bit further here. And the same thing for this lower arm, it's going to approach the asymptote. Here it's going to approach the asymptote. And here is my solution, right? Where they intersect is going to be this solution. So it's going to be close to, well, it's going to be between, say, negative 1.5 and negative 2. So if I was a little bit more accurate with my sketch, exactly where it is, I can guesstimate it's going to be between those two values here, right? And if we're using exactly graphing software, you can find the exact point. But because this is a sketch, a way to confirm, or the other strategy that we can use to solve these equations, is by algebraically solving them. So let's see if we were close to where we are supposed to be. So we just work with our equation, and we want to solve for x. Okay, so you're going to move one over. You get 4. Cross multiply, right? You get 1 equals 4x plus 2. 1 equals 4x plus 8. Move the 8 over, so you get negative 7 equals 4x. Divide both sides by 4, you're left with x equals negative 7/4, which is pretty close to where we are, right? So again, we're concerned about that x value when it intersects. Okay, any questions? Okay, let's do example B now. So we can start with it algebraically first, right? So again, I want to kind of make it so that everything's in the numerator. I have x minus 1 in my denominator. So again, I want to manipulate it so I can solve for x. So I'm just going to cross multiply here. And you're left with 2 equals x minus 2, x minus 1. So I can FOIL x squared minus 3x plus 2. Okay, and then I'm going to bring the 2 over. So then it ends up canceling. So I have 0 equals x squared minus 3x. Okay, and then common factor, and you get x and minus 3. So my two solutions are going to be x equals 0 and x equals positive 3. Okay, and let's see if I can get that to show up graphically here. So again, we want to equate, so you could equate one side to 0 and then graph the two sides and find the x-intercept, or you could graph both sides independently and find where they intersect. So x minus 2 is easy enough to graph. 2 over x minus 1 is the other side. Okay, so let's start off with our rational function here. So again, my 0, my vertical asymptote is going to be at, where my denominator equals 0, which is at x plus 1. So the degree of my denominator is bigger than my numerator. So my HA is at 0, and there's no K value in this one. So it stays there. Okay, and then let's just plug in some values, right? So f of 1, sorry, f of 2. So you would get 2 over 2 minus 1, which would be 1. Or sorry, 2. Or no, 2 minus 1 is 1. 2 over 1 is 2. So you would get f of 2 is 2. And then using symmetry, oh, I found an y-intercept. Okay, and then you could make a banana curve. Okay, and then the next one is this x minus 2 line. So let's dig back to sketching a line, right? So my y-intercept is minus 2, and my slope is 1. My rise over run is 1. So again, we could start, so that's one of our solutions here at negative 2, and our slope is here, 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 right? And then you could so this is going to be y1. This over here is y2, right? So here's one solution, and they should have intersected here. So let me just redraw my banana so that it crosses that way. Okay, which is what we found in the algebraic solution, right? So my graph and my algebra works out, my solutions are at 0 and at 3. Any questions about that one?
Mr. Mariano,
Yep.
when you say your solution is 0, so you mean that's like where they intersect?
Yeah, the x coordinate when they intersect. So 3
Oh, okay.
and 0, because that's where there's an intersection point here and an intersection point here.
Oh, so then there'd be two solutions?
Yep.
Okay. Okay, thank you.
Okay. Which is exactly what we found algebraically.
Okay.
Okie dokie. So the last topic in this unit is oblique asymptotes. So we had vertical asymptotes, horizontal asymptotes, right? So HA is going to be a VA. And so an oblique asymptote, it's the same concept. Our curve is going to approach these lines, but oblique means that they are diagonal. Okay, so it's going to look a little bit different, but again, it's going to approach this line but never touch it, just like these other asymptotes. So this is a really important line. Oblique asymptotes occur. So you kind of have to start this because you always have to think, is this the case where I have to make it oblique? So this happens when the degree of the numerator is larger than the degree of the denominator, where there are no common factors. When the denominator is not a factor of the numerator any longer. So in this case, x squared minus x minus 1 divided by x plus 1. There is 1 or negative 1 is not a factor of the numerator. Okay, so what we're going to do first is do the synthetic division. So once you've determined that this is the case, you're going to use synthetic division to find the equation of the line. So I have 1, negative 1, 1, and then my value I'm going to test is negative 1. Drop 1, negative 1, negative 2, 2, and negative positive 1. So to rewrite this equation, you would get y equals x minus 2, and then 1 over, or sorry, plus 1 over x plus 1 is the factor. So really, this leftover piece is the equation of the asymptote. This x minus 2 becomes the equation of the asymptote. So all we have to do is sketch in the line, and that will be our asymptote. So try to be a little neat for our asymptote. X minus 2. So x-intercept. Try to use a ruler if you have one. really that's all that changes. So instead of a horizontal asymptote, we have an oblique, but the same rules still apply. So whenever the denominator is 0, we still have a vertical asymptote. So at x equals -1, I still have okay, and then again I'm going to test 2 points on either side of my asymptote. So let's go f of 0. If we plug in 0 into our equation, you get 0, you get -1 over 1. So there we go, we get -1. And so that means f of -2. So f of 0 is -1. F of -2 is 4 plus 2 minus 1 divided by -1. So you get -5. Oops, sorry. Okay, and then it's again, the behavior is the same, the shape is just a little off here. So we're going to have this approach the asymptote, but never touch it, right? This is going to approach the asymptote, never touch it. Same idea here, approach and approach. So it's going to get infinitely closer and closer. It's just not a totally horizontal line any longer, but the behavior is the same. I think that's it. But just for general purpose of our graphs, right? We want to draw in our horizontal asymptotes or vertical asymptotes. We definitely want to include our x and y intercepts. So there's none on this bottom banana branch, but there are two x intercepts here. So again, we can use our to find the x-intercepts, we would equate the numerator to 0. So let's just show our work here. So again, our x-int is when y equals 0. So you would get 0 equals x squared minus x minus 1 over x plus 1. And just like in previous examples, when you cross multiply, the denominator just disappears. So we're really only concerned about this numerator and when it's equal to 0. So you get 1, so it's not factorable, got to use quadratic. You get -1 squared minus 4, 1, -1, all over 2, 1. So then you get 1 squared plus 4, so 1 plus root 5 over 2, 1 subtract root 5 over 2. So x1 is going to equal 1.6, and x2 is going to equal -0.6, I think 62, I think. Oops. Okay, last example. So you have 3, 2, so it's in the kind of the wrong order. So for synthetic division, or to make things a little bit easier, again, we could probably factor out the negative so that we don't have a leading negative coefficient, and then we could rewrite this as x squared minus 2x minus 3. Okay, and again, there's no common factors. No common factors, because this would be x minus 3x plus 1, right? So no common factors, and the degree of the numerator is larger than the degree of the denominator. So again, this is going to have an oblique asymptote. So again, just like the previous step, we want to use synthetic division. So I'm going to use the factored out version, 1, negative 2, negative 3. So I'm going to drop 1, you get 2, you get 0, you get 0, and then you get negative 3. So if we were to rewrite this, so remember we factored out the negative in front, so you're left with x, and then subtract 3 over x minus 2. And then let's just bring back the negative, so you get plus 3 over x minus 2. Okay, and again, so after synthetic division, this becomes my equation of my asymptote. And of course, my ruler's not. So x, negative x is this way. Where the denominator equals 0 is still my horizontal, or sorry, my vertical asymptote. So x plus 2. So that's y equals negative x. Okay, and then again, we want to plug in points that are on both sides of my asymptote, right? Just to help us sketch. So let's go f of 3. So 3 squared is let's start with 9. So 3 plus 6 is just 9. So you get 0 on the numerator. So f of 3 is 0. F of 1 is going to be 3 to negative 4. So let's just sketch that out. 3 is 0. F of 1 is negative 4. I'm going to approach my asymptotes. So we could do our x ints and y ints as well. So again, we could do my x int is when y is equal to 0. So again, we just want to work with our numerator, negative x squared minus 2x minus 3. And you got negative x minus 3, x plus 1. So our zeros were x equals, oops, 3 and x equals negative 1, which is here, and oops, sloppy sketch here. Okay, and then our last one will be our y-intercept, which is when x is equal to 0. So then if these are all zeros, so then you're just left with y equals negative 3 halves, right? So negative 3 halves. So the very last step here is pretty simple. It says to solve the equation. So on the left-hand side is the equation that we already have. So if you notice, this is that, negative x plus 3 over x minus 2. So we're just making an equation. So we already graphed the left-hand side, excuse me. We just need to equate or draw 2x minus 6. So back to grade 9 and 10, we're sketching lines. So you have y-intercept of negative 6. And then your slope is 2, so you're going to rise 2, run 1. So this is a point, rise 2, run 1. So it exactly intersects our graph at those 2 points. So if we could just read it, it's going to intersect at 3 and it intersects at positive 1. So let's just prove that algebraically. So the last step is to kind of equate and manipulate this so that we can solve for our x here. So move the x over, you get 3 over x minus 2 equals plus x, 3x minus 6. Cross multiply, you get 3 equals 3x minus 6, x minus 2. Unfoil, or foil, 3x squared minus 6x minus 6x plus 12. we get 0 equals 3x squared minus 6 minus 12x squared, or minus 12x. Move the 3 over, plus 9. Common factor, 3x squared minus 12, or no, minus 4. Plus 3. Then you get 0 equals 3x minus 3, x minus 1. So x equals 3, x equals 1, which is what we had in the first place, right? So we've proved it algebraically, and then it matches our graph. Okay, I'm going to stop the recording.